Welcome to this lecture number 4, and this is module number 1 and unit number 4, that is classification of differential equations. What is the learning objective of this particular unit? At the end of this unit, a student will be able to classify differential equations based on physical behavior, completeness of problem definition, and linearity. Classification based on physical behavior. First kind of problem that is called as equilibrium problem. As per Tannehill et al., problems in which a solution of a given partial differential equation is desired in a closed domain subject to a prescribed set of boundary conditions. In this one, this closed domain is important point, and there should be only boundary condition. In our previous unit, we have discussed about initial conditions and boundary conditions. So, for equilibrium type of problem, we need one governing equation and corresponding boundary condition. This kind of problem is also known as jury problems. So, boundary conditions act as jury. Generally, these problems are steady state problems, and solution is always smooth even if there is disturbance. So, from all sides the boundaries are defined. Mostly these problems are steady state problems. Let us consider one example where we have one sheet pile at the middle, and this is our ground surface as well as water level. In this case, this is your ground surface and this is our water level. So, obviously there will be flow from this side to left to right, and this problem can be defined in terms of the governing equation, that is del 2h del x2 plus del 2h del y2, that is actually Laplace equation, and in terms of Dirichlet boundary condition and zero Neumann condition. Dirichlet boundary condition is applicable for this boundary where our head is specified. Again, it is applicable for this boundary where head is known. In the middle, the sheet pile acts as no flow boundary. That is why zero Neumann boundary condition can be directly applied for this problem. So, this side, that means left and right side, also it can have the specified head condition, or if you have no flow boundaries, then also things are defined. So, we have one differential equation and boundary conditions. So, in this case the problem is space dependent, this is not time dependent, that is why this is steady state problem. Second kind of problem is called as marching problem, where the problems in which a solution of a given differential equation is desired in an open domain subject to prescribed set of initial and boundary conditions. Generally these problems are transient or transient like problems, and the important point is that not all marching problems are unsteady problems. So in this case we need one governing equation, one initial condition and boundary conditions for the hydraulic system. So initial condition means that your time domain, one side your values are defined but the other side is open, that is why this is open domain problem. So mostly these are transient problems. Classification based on completeness of problem definition. This problem is called as well posed problem, where solution of the problem exists. Second condition is solution of the problem is unique, and third condition is solution depends continuously on data and parameters. If we change the initial condition or parameter values, obviously there should be change in the solution. Otherwise the problem is called as ill posed problem. That means if there is violation of any of this condition, then classification based on linearity. Classic example is this groundwater equation for confined aquifer. So obviously this equation is linear in nature because there is no multiplication of dependent variables. Then there can be nonlinear problems, maybe this momentum conservation equation for surface water. In this case we can see that this q square term is there, which is nonlinear in nature. So in this case we can say that equation is nonlinear. If we consider our hydraulic system, most of the differential equations we can consider as linear second order partial differential equation. So if we have two independent variables and phi is the dependent variable, then we can write this equation where A, B, C, D, E, F, G, these are coefficients, and these are actually functions of x and y, otherwise these values are constant. Highest partial derivatives determine the nature of the equation. So in this case highest partial derivatives are 1, 2, 3. So from this equation we can get the characteristic equation which can be written in this form, and depending on sign of discriminant, that is b square minus 4ac, the equations can be classified. So, classification of second order PDE, first is parabolic, b square minus 4ac equals to 0. So, transient one dimensional groundwater flow equation in confined aquifer, this h by t del h by del t minus del 2 h by del x2. In this case, h is a function of t and x only. So, if you compare this equation with our linear PDE equation, that is x and y, so we can find out the coefficients a, b, c, and based on that we can comment on the nature of the partial differential equation. So, in this case a is 0 because the coefficient of del 2 h by del t 2 is 0, b equals to 0 because there is no cross term, c is minus 1 which is the coefficient of del 2 h del x 2, this is actually minus 1. So, obviously b square minus 4ac, this term is 0. So, we can say that this equation is parabolic in nature. Then comes this elliptic equation where b square minus 4ac is less than 0. Steady two dimensional groundwater flow equation in confined aquifer, this is Laplace equation. Again, if we compare this equation with our original phi xy, this is actually x h xy. So, we have coefficients 1, 1, but for cross term the coefficient is 0. So, a is 1, b is 0, c is 1. So, b square minus 4ac is minus 4, which is less than 0. So, we can say that this equation is elliptic in nature. Then hyperbolic equation where b square minus 4ac is greater than 0. One dimensional wave equation. In this case we can see that the coefficient of u, which is a function of t and x, is 1, and in this case it is minus 1. There is no cross term available for this equation. So, obviously we have a equals to minus 1, which is coefficient of u del u by del x2, b is 0 and c is 1. So, this is b square minus 4ac, which is positive in nature. So, we can say that this equation is hyperbolic equation. Now, eigenvalue based classification. So, we can have multiple independent variables for the differential equation. So, let us consider a PDE where we have n independent variables x1, x2 to xn, and aij and bij, c, d are coefficients again. These are either functions of x1 to xn or these are constant values with the assumption that the cross term we have symmetry for this coefficient which is corresponding to the higher derivative terms, we can construct a matrix A lambda, and this is symmetric in nature. Symmetric because in this case we are considering that the coefficients of the cross terms should be same. So, with this assumption, the eigenvalues of A lambda are the values of lambda that satisfy the equation A lambda minus lambda into I, which is identity matrix, and determinant of that should be 0. If we can solve this equation, we can find out the values or value of lambda depending on the order of equation. So, equation can be classified based on sign of eigenvalues lambda 1 to lambda n of the matrix A lambda. For parabolic equation, one or more 0 eigenvalues. If we have elliptic equation non-zero and with same sign, that means lambda I is greater than 0 for all I, or lambda I less than 0 for all I. If we have hyperbolic equation, then non-zero and all but one are with same sign. That means for a particular jth eigenvalue, this is less than 0, for others it will be greater than 0, or combination can be lambda I is less than 0 and lambda j is greater than 0. If we consider examples for parabolic equation, we can take the same transient 1D groundwater equation in confined aquifer. In this case, if we construct the coefficient matrix A lambda, then we can see that this 0, which is diagonal term A 1 1, 1 1 means there is no coefficient for del 2 H by del T2. This is 0. So, obviously this is 0, there is no cross term, that is why 0 values corresponding to cross terms, and minus 1 as coefficient of del 2H del x2. So, obviously eigenvalues lambda 1 0, lambda 2 minus 1, which is less than 0. So, one of the eigenvalue is 0. We can say that equation is parabolic in nature. If we consider elliptic equation, again with the Laplace equation, the coefficient is 1. In this case also this is 1. So, if we consider the coefficient matrix, this is 1 1 1 1 and cross terms are 0 0. So, if we find out the eigenvalues, lambda 1 is 1, lambda 2 is 1, both are greater than 0, that means they have the same sign and both are non-zero values. So, we can call this as elliptic equation. In case of hyperbolic equation, that is wave equation, we can see that the coefficient is 1, here it is -1, and with this information if we proceed we can construct the coefficient matrix. This is 1, -1 and cross terms are 0. So, lambda 1 is 1 which is greater than 0, lambda 2 is -1 which is less than 0. That means the opposite sign is there and both are non-zero values. So, obviously we can say that the equation is hyperbolic in nature. So, let us consider a form of differential equation with a general variable phi. In this case phi in general form it is a function of x, y, z and t. Gamma phi and epsilon phi, these are problem dependent parameters, and this lambda phi and epsilon phi, these are problem dependent parameters, and gamma phi, this is a tensor and this is equivalent to diffusion tensor, and f phi 0 or f phi others, this term considers other forces, and S phi is the sourcing term. So, we can use this general form of equation to represent all of our hydraulic system related problems. So, example is mass conservation equation, that is del u del x del v del y del w del z. In this case we can see that lambda phi is 1 and phi is rho and which is constant. So, obviously the temporal term in the left hand side is not present. Epsilon again that is 1, and this dispersion tensor, dispersion coefficient tensor, this is again having 0 0 values. That means all terms are 0 in this case. So, there is no diffusion term, only advection related term in the left hand side. So, other force, this is 0, S phi is 0. So, if we use this parameters, forces and sourcing terms, then we can get this mass conservation equation from our general equation. Again if we use this lambda equals to rho, phi equals to u which is velocity in x direction, epsilon equals to rho, and this diffusion coefficient tensor as with dynamic viscosity, and body force including pressure and this gravity force, S phi is 0. So, for this momentum conservation equation we can get this form for incompressible fluid flow, because we have considered constant value of rho epsilon. So, obviously, the rho will be in multiplied form on this side, and that rho can be transferred here, so that we can get this incompressible fluid flow x direction momentum conservation equation. So, with this information we can proceed and further for concentration, which is scalar transport equation. Again, lambda phi is 1, phi is eta c, eta is porosity, c is concentration, epsilon phi is 1. Again, for 2-dimensional case, this is diffusion coefficient tensor, other forces are 0, and sourcing term, that is Qs Cs. So, this is actually sourcing term, and this is our advection term, these two are related to diffusion term, and this one is temporal term. So, obviously, we can get the concentration equation from our generalized equation. So, we can utilize this generalized equation and we can get the discretization for that equation, so that we can use that general discretization for all kinds of problems. So, this is the end of module number 1. Next module will talk about numerical methods.